You, Howard and Mario.
Debs, thank you very much. So let me just start sharing. Okay, all right. So I'm getting confused with all of my screens. All right, great. So this is the session for today, and what we're going to be focusing on is what the insurance practice or claims processing refers to as anomaly detection. So really just to maybe take you back through this case study. This case study was about automating insurance claims. And so you can see here the business process is first notice of loss, then we do the claim intake and validation. We process evidence, and we then do fraud detection. So the idea here is that we would build a chatbot that would engage with the claimant, and that may be the actual claimant or maybe a broker, and that person would be submitting the incident or the claim on behalf of the claimant or the claimant themselves. And whilst they are submitting this evidence, they're being guided about what they may need, what needs to be provided, photographs, OCRs, recordings, police reports, hospital information. And then we go into fraud detection and risk assessment. And once we pass through fraud and risk, we can go into making a decision about the claim, settling and paying the claim, and then customer communication. So this is the process we're working on. And what we're trying to do is explain how this one process has all sorts of links to different frameworks. Mario had a great session last week where we spoke about the challenges between chatbots and LLMs and data privacy. So we just showed some of the connections there. Now, what you're seeing here is a UML interaction diagram, and this comes from Accord. Okay, so Accord is the insurance industry standard, and this is the business process, and these are the messages and the message types that are actually sent, and it could go across multiple parties. So there's FNOL, which it's known as, and there's the claim report, then DRI, the evidence and claim movement, and then the risk scoring, fraud detection, claim decisioning, and so we go. So there's the UML diagram of what happens. Okay, and then what we did as well is to say, well, okay, now we've got this business process, but then where do we map to the different DMBOK knowledge areas? So we can see this aspect here involves data governance, data quality, and there's a whole lot of mapping. And then where do we map to things like reference and master data? So on FNOL, we would need to do that entity resolution. We all know with master data, you've got to resolve the entity. So we'd need to resolve the customer, we'd need to resolve the policy, we'd need to resolve assets. And as we go through the process, there's different requirements on reference and master data. So even though we are handing this over to a chatbot, these are things that we still need to support, and we require the support of MDM to deal with this stuff. And then we go a little bit further, and now we've got the different mappings. And can you see here all the different frameworks that may be applicable to you if you were to implement an NLP chatbot, a digital form, identity proofing, OCR, computer vision, entity resolution, predictive modeling, coverage and eligibility, rules engines, machine learning, knowledge graphs. So these are the possible things that you could make use of, the possible AI techniques of automating, and then these would be the corresponding frameworks that you would need to be aware of, and you'd need to check that this how it applies to your environment and what you need to do. And then right at the end there, you can see even the link that insurance companies have with BCBS. across their different, and IFRS as well, the IFRS reporting. Okay. So lots and lots of different things that come together. And when you go into the AI environment, and I think it's important to say that, please, this is not just about AI. We need to pay attention to data management. We need to pay attention to cybersecurity, to corporate governance, to ethics, to systems, records management, documents, OCRs, all these type of things. And we sort of need to know what we're touching on and who needs to be doing what to make this succeed. And so there's lots of different moving parts. And that's where the tool like Mario has, in terms of the ability to take a business driver, build a use case and deliver on the use case, and then make sure you're paying attention and you're managing the risk in the background. Okay. So amazing to see when you choose to do something, these are all the red lights that come up to say, have you thought about this? Have you dealt with this? Have you dealt with that? And when you're setting up a program and when you have different maturity levels, you need to tackle things in different orders. And what we're desperately trying to do here is to say, here's an objective, these are the use cases, and then these are the things you need to pay attention to on the left-hand side. ISO regulations, corporate regulations, AI Act, what maturity you're in, how many people you've got, what is the NAII index. So in Saudi, they've just released the National AI Index, and organizations need to comply with it. We've got DCAM, we've got risk. And so it gets a bit scary when I've got 1,000 things to do. And I've got to pay attention to all this stuff, and I can easily get lost in this framework world and not do any work. And so we're trying to avoid that thing. So basically what we're saying is, what are the business ambitions that relate to a strategy? We select a use case, and then we understand the different constraints that we need to adhere to, understand our capabilities, and then recognize the AI governance requirements. So these are all the challenges that we face. Okay, now I didn't want to, what we did the last couple of times was work with Mario on showing how he puts all of this stuff together in Pradago. But now what I'd like to do is actually show you how I've approached it using a level of data quality. And I just need to jump to the right place, and I'm now not sure exactly where it is. So please excuse me whilst I just check up on my deck where we're sitting. It's anomaly detection. Here it is, 100. Okay. Okay. All right. So this is the anomaly detection. And when I was going through this, I realized how powerful and how many challenges we have on data quality. And I don't know how many of you have done that reasonableness dimension. How many of you have actually implemented? We see it documented in the DMBOK, but what we don't see a lot of times is how can we make use of it? Okay. And when I was going through the anomaly detection process, I realized that, wow, this is very valuable, because when we use AI techniques to see anomalies, it's doing the same thing as a DQ reasonableness validation. If you didn't have AI, what you typically do is define business rules. So if it's between this and this, then we have a challenge. If things haven't changed since the last time, then maybe we need a business analyst to phone the bank. And I remember doing that in a central bank, where we would get the BA 100 every morning, and then we'd have a rule to say, well, there wasn't much change in this line item. We're expecting a change. Why hasn't it changed? And then it would go to an analyst, and the analyst would phone the bank, and they would talk about what the challenge was. So typically, a lot of the times I was working at a single CDE, and now with Anomaly, you're actually working with multiple CDEs, multiple features. So you're having to understand all of these different relationships. Okay, so and just to be able to share with you on this is a Power BI that I've built to be able to do the anomaly detection and the different features that I'm working on for a claim that can help me detect an anomaly would be the claim amount, the duration of the claim, the claimant age, what age the claimant is, the policy duration, and then a previous claim. How many previous claims did we have? Now, very quickly, when you start to look at these different features, you can see, for example, claim amount can go anywhere between 100,000 and R0. Okay. And then what we've got is for the number of days, it could be from 400 to, and there's an outlier here of minus 200. Or the age can go from 80 to 0. Now, I'm sure we're all aware of the situation where if you put all of these features together on a single histogram or graph, this the claim amount will just render the duration days or the age or the previous claims. It will just disappear on the graph. And so we've got these almost orders of magnitude different between the features, and now we need to look at a way of comparing these features and not have one feature outweigh another feature. Okay, and so this is the technique that I've used to work through these anomaly detections. Okay, so working through this process of trying to automatically flag an anomaly. Now, when I say flag an anomaly, what you're saying is this thing doesn't fit the pattern. So I need to call in a human. I need to have human in the loop, and I need to talk to this human and ask them to validate that this is an anomaly. We can't pay the claimant out. And we were talking last week about what happens if this is funeral cover and people don't have any money and they desperately need money to have the claim paid out. That's the challenge. And if you now start deferring it to humans to check out, then it gets longer and we can adversely affect the people that we're working with. All right. So here's the recipe that I've put together for anomalies. Sorry, I can't see. I've only got one screen and I can't see if there are any hands up. Maybe I'll just pause here to see. Does anyone have any questions? Are there any questions about what I'm trying to do, how this relates to data quality? And of course, when you're doing AI, it's critical that your quality of your data is good. Otherwise, you're going to make some terrible decisions. Any questions?
No,
Okay.
Howard, all good so far.
Okay. Thanks, William. Thank you very much. All right. So let's go through the anomaly detection recipe. Now, what I've done here is, and of course, I'm always concerned about having test data. So where would we get our lots and lots of test data? AI has this need for large amount of data. One of the data quality dimensions for AI is large amount of data. If you look at the Wang dimensions, they talk about that you have to have a significant amount of data to validate your models. And so it's not easy to get this information. And so I put my first step in here in showing you how to generate synthetic data. Has anyone heard of synthetic data? William, have you heard of synthetic data?
I have, but I'll be honest, I'm not entirely sure how you get it. I presume you have it auto-generated, but I'm not
Yes.
sure how that process works.
Okay. So, and I'll take you through this, but basically what you do with synthetic data is you analyze the patterns of the data in production. You then bring those patterns into a algorithm, and then you can say, okay, generate me 20 million records based on this pattern. Okay. And so it keeps the pattern of production, and now it creates you a synthetic data set in the test environment, which is great from a PII point of view, not having to expose this data to a data scientist. And one of the things that struck me about this was when I was working on one of these central banks, we built an innovation hub, and one day I was talking to the data scientist and he says, you must see all the data I've got. And he had data from everywhere, just about every single department. He could see everything, and it was all production data. And it's like, oh, I think we got a serious problem here. This guy he's able to see every piece of data in the organization, and of course that's not very sensible. Okay, so basically I create the synthetic data that adheres to the normal pattern, and then I have to inject anomalies. So I have to create problems, and then I have to check, well, does my training and does my anomaly detection actually pick up those anomalies? And if it can't pick up the anomalies, then I've got a problem with my anomaly detection. So there's a great way of testing that that your detection's working. Now, what's also interesting is that I find that I can actually look at anomalies on the clean data and then start saying, oh shucks, these claims look funny. Then you go to an SME, you go to a business person, and you say, well, please can you double check these anomalies? And you have this process called labeling, where you label the data to say this is an anomaly, this is the type of the anomaly, this is why it's got like that. And we now start teaching the machine and teaching the model to recognize these patterns. That's what we're trying to do. And I'm hoping you can see how this applies to data quality. Estia, I know you got your master's in data quality. Do you remember the reasonableness dimension? Have you ever thought of, and then implementing it and or dealing with that data quality at a record level and a table level where you're checking lots of different relationships between fields?
So Howard, here's the very honest answer to that. Yes, I would love to think about that, but a lot of companies are just not even at that point.
Sure.
So a lot of them, we're checking completeness,
Yes,
which is a sad part to be at. So I'd love to get to a point where we're checking reasonableness, but this is a good conversation because that's a pre-stepping stone for AI. So you can't bypass reasonableness or data quality and just implement AI. So the sad answer, sorry.
Okay, no problem. And what I like about this is it's amazing how when you link to a business driver, that all of a sudden the lights come on and say, oh, shucks, I can now use this to help me with my data quality. So I can use some of these techniques to pick up data quality issues as well. And it's amazing how you can learn from these different areas. Okay.
I do want to mention something. So I was looking to see if I can find like a reference article or something. So I know like City of Cape Town has a data science team, for example, which I'm very impressed about in general that City of Cape Town has that. So I know that they use anomaly detection for certain processes as well. So I'm actually very curious to know more about their details if, they're going through these steps as well. But I know they've used some of this.
So it's actually interesting, Esti, because I'm talking with one of the guys from the municipality, the Cape Town municipality, and he's asked me to do data quality in AI. So
awesome.
So that's now 2nd or 3rd of October at the Data Fest at the Windmill. So
awesome.
we'll be having a workshop there. Okay, so let me go through the process again. Generate the synthetic data, then split the data up into this training, testing, production, and I'm going to give you some more understanding there. Then you normalize the data, and then we look for the anomalies, and then we do a visual inspection. Okay, and let me show you the end result. The end result looks something like this. This is my final visualization. and here it is over here. Okay, so here we can see across the different categories of incidents. We've got accident, fire, medical, other, theft, and then all incident types. And you can very quickly see that there are these big outliers. Can you see this one over here? That's sitting at a claim amount of 5,000. And we can make use of these. So what I've done is I've actually got 3 scoring models. I've got one class SVM, isolation forest, and autoencoder. And if all 3 pick up an anomaly, then I get 3 points and my risk level is high. If I only get 1 person detecting it, then it's low. And then if I get 2 detecting it, then it's medium. So we can work out where these different areas are. Now, the gray dots are where we haven't picked up any anomalies. Okay, so let me just switch that off and I can show you what it looks like. Okay, so here you can see in the training set that doesn't have any anomalies, I've got a couple of funnies, but there's my grouping. Those are all, that's the grouping of the normal data. And I've got some challenges where the routine has picked up an anomaly. So in the normal data, not in the one that I injected, there we're picking up some little funnies. Now, this is actually quite hard to understand why it's a funny, and that's going to be our next challenge is when a routine detects that it's funny, how does the SME explain why it's funny? So that's going to be the next challenge. But I'm hoping you can see that the visualizations are really nice to show me, you know, what these different areas are. And there are these wide outliers that are sitting there. And it's a nice way of visualizing that. Can you see how you can detect it with multiple routines and then visualize it for the business person, and then you can isolate where these different elements are. Any questions, observations on that?
Can I make a question or observation? So
Sure.
I realize so the dashboard having is quite nice because then people can see the output.
Yes.
Is the intention almost with a lot of this, and I think you did mention it before, like to identify ones where, you know, what should the people check? You know, so it's not
Yes.
a automatically kind of, you know, you won't get paid off, but a human needs to go check
100%.
this.
100% is that you don't want to say no unless you can
Exactly.
explain it. Okay, so whilst these anomaly detections have done a great job in detecting it, I don't know, it may be a valid thing. You know, we can't, we have to go to a human, and that human has to interrogate it and come up with the answer, and maybe phone the person, you know, and look at different, analyze it in more detail to be able to pass a judgment. So it wouldn't be an automated no. It would be, these are the anomalies for this claim that you're talking about, and can someone check it? Now, the difference is if it's not an anomaly and the risk is none, then fantastic. Let's just pay the claim. Now that comes with its challenges, but that's what we're trying to do. Is if the person's got to bury their father or mother or whatever it is, they can't hang around. They really don't want to be kept waiting for whatever it is. And so we've got to get that payment done as quickly as possible.
Cool.
Okay.
So,
William has
what I find interesting about this, Howard, is that when you do take it through to your SME, it would be good if they discover false positives, because obviously these are positives, right? If they discover false positives, because then you can go back and relook at your algorithm to see maybe the data's changed, maybe I need to adjust the algorithm, because otherwise I'm not going to see any false negatives either.
Well,
or I'm going to be potentially mislabeling things.
So you're going to see now, I'm actually going to show you what's called the confusion matrix. Okay. So we actually have this concept called the confusion matrix, and there's something called an ROC curve. And what that ROC curve and confusion matrix is, what is, they have two metrics on these models. What is the precision of the model to detect a positive? So are you detecting true positives? And then in some cases you may be detecting a false positive. That's precision. And then recall is, are you picking up things that are appropriately negative? So we then build what's called the confusion matrix, William. And the nice one is when you got a positive or a false positive, because you then can allocate it to a human. Then the horrible one is when you're missing and you're not detecting anomalies, and then the organization's losing money. And that's the one that you can't do much about until someone sees it or you run a different routine. So let me try to show you some of that I've done. But you're right, William. It's that one challenge that we're going to get into. Okay, so if you can hold that, I'll hopefully share this with you. So this is my routine that I do. And notice this labeling is very important. So I generate the synthetic data. I inject the anomalies, extreme claim, unusually long durations, implausible claimant age, excessive policy, high previous claims. I inject it into the data, and there you can see I've got two truths. Okay. And what that is saying is I'm testing to see whether the data scientist model, the training, will detect it. If the training model does not detect it, then we know we haven't got the right sensitivity or whatever it may be. We've got some challenges. So that's our first test. Our first test is inject anomalies. So this is the Python code. Please understand that this Python code is actually being integrated into my Power BI. Okay, so let me show you what's happening there. In this Power BI, I run the synthetic code. I actually generate the code. So I'm going to just take you into, there's the code, edit the query. Sorry, 1 moment.
Yes,
So okay.
check minibar.
Yeah. Okay. So can you see, here's the source, and this source is actually Python code. So here's the Python code that's actually been generated that I'm showing you in there, and then I can link it in here. And in the Python code, I can actually point to the data set, and in this one, and I'm going to show you how that works. But I can take that sample data from live, and I can generate a synthetic data based on the live data. Okay. So let's see how this works. I've asked it to generate 10,000. I'm using a sample data set from production. It has got categories of incident, and I'm using its shape, the mean, the standard deviation, all of these things. I'm using the shape to generate the next set of normal data. And so these are the different features that I'm using, and I'm using this generate base record algorithm, and I'm using statistics to be able to create all those different records with random integers and things like that between the different areas. And here I'm able to generate the synthetic data. Okay. And it's also being grouped by the incident type. So incident type, for example, accident, fire, whatever it is, there's a shape per incident type. So there's not a shape across all data. It's a shape by incident type. The shapes are different. So an example of that, an average for accident is different to the average for fire. It's different to the average for medical. It's all these different areas that we need to be careful of. Okay. So this is basically what we do. We have to look at creating the anomalies, and then you've got three different types of anomalies. One is a point anomaly that's extreme claim amount, unusually long duration. We've then got collection anomalies where I'm actually creating 20 records that sit together in the same pattern, but they're out of line with the main pattern, which then can confuse the model to say, oh, well, this pattern looks good. Okay, but it should pick it up. And then we've got contextual, which is it's very close to the other pattern, but slightly different. Okay, so it's quite amazing how much you need to pay attention to in generating and injecting the anomalies. Now, what you don't do is you never inject the anomaly into the normal training set. The normal training set must be clean. And that's problematic in itself in terms of how do we know that that normal training set is clean? We start somewhere and then we keep on refining and working it through. Okay. So here's the Python code to say, okay, my training set must be 70%, 70%, my test size is 20%, and my production size is 10%. So 7,000 records, 2,000 records, and 1,000 record make up the 10,000. Okay. And then right at the end, we put all these anomalies in, we join them all up, and then we shuffle the data. So we don't have all the anomalies sitting from ID 10,000 to whatever it is. We got to try shuffle them and get them in. Okay, so maybe just to pause there, any questions in terms of how that synthetic data has been generated, what we need to pay attention to, and how I've been able to create all of this data without really reading anything from production. So I don't need to go and get 10 million records from here. I can use the environment. Yes, William.
Well, I suppose one has to be really close to procedural changes, variable changes in the business rule changes, because then you'd have to go and rebuild your synthetic data based on new changes. But then when you do your query over time, you'll need to apply the different versus of normal, from period A to B. This was the set of variables. B to C, it was a different set of variables. You probably have to do something to that extent. I know that that's not the complexity you're showing here, but over time one would have to manage something like that, right?
Okay, so what you're referring to is what's called a ML drift, where the features drift in their structure. Now, even though they drift, what you'll find is that you'll still have you can have a time-based feature in your algorithm, William. So it will also be part of the pattern for that time. So you don't really need to complicate your code. You would just add a date parameter into your feature list. Does that make sense?
Yeah, it does. Thanks.
Okay, so where you 100% correct. When we've got what we need to do is when we start the model, we'd say this is the shape of those features at this point in time, and then we constantly monitor the shape of what it was when we did the training, and if that changes significantly, then we have to retrain the model. Now, what we are seeing with some of these routines, William, is that we can what's the right word? We can train it very quickly in that situation. Okay, so it's amazing what can be done, and you have to constantly be paying attention to, well, is it possible to quickly train in terms of where we are and detect it? But your point is still valid. We need to understand the shape of the data when we train the model, and when do we need to retrain the model to get a new shape? Does that help you?
Yes, but what I was really alluding to is that the folks that are busy with this kind of work really need to be plugged in to the change control and the change management of the business.
Not necessarily. So what we constantly do is we record the shape of the data when we start. DQ monitoring constantly looks to see whether the shape has changed significantly, and it raises an alert to say,
right.
guys,
Okay.
we're out of line.
That's where you tackle it through the DQ
steps.
Okay.
You actually record a lot of metadata on the shape when you start. you record that shape, and then you constantly compare it to the current shape. And if there's a significant deviation, you call for a retraining.
So if the DQ stewards who are close to the business and what's going on, if they hear of these changes, they will go and have a chat to the person who's working with the model, and then there'll be a conversation. That's being a bit more proactive.
So of course, what we want to do is make sure that the SMEs are involved in this all the time, and they have a basic understanding of the shape that was discovered at that point in time. So you're really getting to lift up the SMEs, because remember, they are going to be the ones that have to explain the anomaly, and they need to understand what has changed from the normal shape, what has changed to the anomaly shape, and why is there a difference. So they'll constantly be looking at this. They won't go to sleep on it, or they should certainly not go to sleep on it if they constantly called on to explain why something has changed or why it's an anomaly.
Okay, cool. I just want to understand which people would be involved to make sure that happens. But if the SME is involved, then obviously they're going to be tipping the guardrail.
Correct. So of course, there's automated monitoring that would do the DQ in the morning, the same way as we do DQ monitoring of reports of data that gets loaded in the warehouse. We'd have to refresh ourselves and go through that. Okay. Cool. So just and here you can see that this is what my data looks like. I've got 10,000 records. I've got 9,700 that had no anomalies. I've got 100 with points. I've got 100 on contextual, and I've got 100 on collection anomalies. Okay, and there's the distribution of the claim amount. So that's me constantly trying to check that my auto generation is working. Okay, so that was labeling and shuffling. So all the time, as soon as an SME picks up an anomaly, they've got to go and label that anomaly to say, yes, this is now an anomaly, and this is the reason for the anomaly. And so that we can train the machine to detect that anomaly again, something else that fits that pattern, it would detect again. So we have this process of injecting anomalies, and then we train the machine, and it detects not just the anomaly ones, but also weird things happening in the data itself. And I'm going to show you how we do that as well. And then send it off to the human. The human validates, yes, this is an anomaly. They'll come back and they'll tell you what that problem was, and they'll label the record so that the machine recognizes it again. Okay, so this was one of the questions you asked about precision and recall. So we have this concept called precision of the model. That's talking about false positives and false negatives. And precision says, of all the claims the model flagged as anomalies, how many were anomalies? So precision is equal to true positive over true positive plus false positive. And then recall is, of all the actual anomalies in the data, how many did the model find? So that's true positives over true positives plus false negatives. And then we have what's called this F1 score, which is 2 times precision multiplied by recall. So to try to explain it to you, this is what it's all about. It's called a harmonic mean. The F1 score is called a harmonic mean. And here it's a really nice example with the arithmetic mean. So let's say precision is equal to 1 and recall is equal to 0.1. The arithmetic mean, if I just do the average between the two, I get 0.55. But if I use the harmonic mean, I get 0.18. So what this harmonic mean is doing is that it doesn't worry about large values. It's less influenced by large values, but it punishes low values. So if my recall is really bad, then I get punished. And that's the F1 score of the model. It's now deteriorated to 0.18. Okay, so it's telling us that this model is not performing well, and we have a problem, and now we need to go and retrain it. William, does that give you an idea of what's happening?
Yeah, it's actually very helpful. Thanks.
Okay, now what's interesting about this, F1 is the first score that they have in statistics. So the reason why they call it F1 is they use these harmonic means, and then they have different ways of calculating the mean and highlighting different deviations from that average. Okay, so the next thing that we have to be doing on a regular basis is constantly testing our algorithms to can they find the do they have the right predictive power, and they're not random guessing. So you can see here that if I'm getting a lot of true positives, or my true positive rate, then I'm sitting above this line. And if I'm getting below this line, then I have no predictive power and the model's just guessing at anything. And when they random guessing, then I'm generating lots of work for the humans. The humans are constantly checking everything, and we get a lot of this false positive rate. Okay, so here we're driving the humans crazy. They're constantly having to look at it. And we got to get out of that loop. So there's a nice way of checking it. And of course, one is the perfect classifier. This will detect every single anomaly and there'll never be a mistake. Now, not all routines can get there. Hardly any can. And we just want to see how close our algorithm is towards that perfect classifier. I'm hoping that's making sense from a visual point of view. Any questions on that? Just want to maybe pause there.
All good for myself.
Okay. All right. So this is what we refer to as a confusion matrix. And the confusion matrix is actual normals and then predicted normals or predicted anomalies. Okay. So of the actual normals, what did we predict to be normal, and what did we predict to be an anomaly? And then actual anomalies, what did we predict to be normal when it's an anomaly, and how many times did we predict that it was an anomaly and it was an anomaly? So there's your confusion matrix, and it looks something like this, and you're constantly having to monitor all of these confusions that are happening within the area. And what we're trying to do here is pick up the false negatives. Too many anomalies are missed. This is the danger. This is where the fraud detection is actually not helping. Okay, and we're passing everything. And then we probably may think that it's actually better that we just slow down the approvals of the claims and we get people to look at them. And they start looking for things, and the model's not really helping. Okay, which is what you may need to do if your routines aren't detecting this appropriately. Okay. All right. So now just to share with you the Python code, or the code that I use to with this one class SVM. Okay, that's a vector model. Okay. Now it's actually really easy. This is all of the code that I've done. And it's actually showing you here in Power BI. There is my Power BI model, and this is the way it's done. There's the ROC curve. Okay. Now, I'm not sure why it's taking its time. I think I'm running out of memory on my machine. Okay, so there's your perfect classifier on the left-hand side. And then this is quite interesting. Can you see here, I've got a really low ROC curve for this one class. Okay, and when I ran it, I really got a fright to say, this is random guessing. Remember that visualization I showed you? Because the graph is so far down here, this is random guessing. And so I went into panic mode to say, oh, shucks, I thought this one class was doing pretty good when I was looking at now it's doing nothing. But what this is actually showing you is this is the ROC curve for just the normal data that has no anomalies in it. Okay, so what this is actually saying is that this is what I considered to be normal, but it is picking up anomalies. So it is detecting very low anomalies. So in theory, if we had a normal data set that had no anomalies, then this would be a flat line at the bottom. And so almost the exact opposite to where we detect every single anomaly. Okay. So that was quite a challenge for me to understand how come this thing's going the other way. I've never seen a graph that dropped down the bottom there, but then what I did in the Python code, just to show you what I'm doing, is can you see here that I'm looking at just give me the normal data. I don't want to see the anomalies. I just want to focus on the ROC curve for the normal data. I run the training on that one class SVM, and we use something called a decision function, which gives you the distance. And then I do a plot on the ROC curve. So what it is telling me now is that some of my normal data has anomalies in it. And so that was the big question. Like, what happened here? Why was this? And it's really because this is picking up anomalies in the normal data set. Okay. Right. So normal records incorrectly flagged. That should be low. Okay. That's what we're working on. Any questions? I feel like I'm losing people. Any comments, questions?
I don't think you're losing us. I think what's happened here is that you've really taken an area that virtually none of us have good knowledge on, and you're teaching more
Yeah.
than and so everybody's listening because they're finding
Right.
it really, really good. So yeah,
Great.
don't worry about
So-
not getting feedback.
So I mean, I think what is mind blowing to me was the situation of, my goodness, this is how powerful these anomaly detection routines are, and they're not difficult from a coding point of view, right? So this is not this is sorry. The code that I'm using to get this thing, I mean, it's like 50 lines long, and you can read it and you can understand what it's doing. You can understand how it's injecting the anomalies. It's not a hectic code. It's not like pages and pages of code. You can understand how the ROC is working, how the confusion matrix is coming about. And there's the ROC. Yes, Paul.
Thanks, Howard. I just want to play back to make sure that ROC curve was down. Because normally, as you said, right, normally the ROC curve needs to be to the top left.
Correct. Yes.
And the reason why we saw this is the data set that it was looking at actually contained no anomalies because it was your normal set, right? So
Yes.
is that it?
Yes.
Do I understand that correctly?
It's 100%. So we spent a whole lot of time getting the right set of data, sampling the right set of data from production, getting that structure. I then generated the synthetic data on that structure. And then I said, okay, well, find me challenges within that data and ignore the possible anomalies. So that's why it's really low, and that's why I'm picking up some of those false positives. Did I explain that well?
Yes, thank you.
Okay. So yeah, fascinating in terms of also then going back and reassessing what you consider to be normal or what you consider to be your training data set. Is my training data set clean? You know, if I had a lot of these, if I had an ROC curve on my training data set sitting up here, we would be in trouble because it's full of anomalies.
Yes, full of anomalies, and it's not picking.
Yeah.
It's not picking up the right things. Yeah.
Normal is saying to the model that this is what good claims look like. Okay. Now, if it's full of anomalies, then I'm teaching it that good claims are or bad claims are good claims. That's what I'm teaching it. Okay. So that's the power of what the process that we're going through. And of course, you know, you'd want to be continually working with the SMEs to say, well, you know, what are these ones down the bottom here? You know, what are these things that it's picking up on that we're not sure of? Now, I can show you an example of that. I also created what's called a statistical threshold. Okay, sorry. So I've just loaded in Power BI. I've loaded up a link to the thing in Power BI in the cloud. Yes, Esti.
So I suppose that would be one of the biggest challenges, is to know your data so well that you already know this is good quality data or bad quality data. You can't really
Yes.
have data to say, I know something is odd, but I don't really know what is odd.
Yeah.
Right?
Yeah.
That's also then it's not gonna give you insight to what you don't have. You already kind of have to know these are the bad claims, and then teach it. This is what
No,
bad
this
claims
is
look like.
yeah. This is you. This is where I'm battling mentally at the moment is when I look at these 6 or 7 features: claim amount, duration days, age, policy, and previous claim, and I pick up some anomalies, and then when I look at the data, I look at this thing and I say, I don't really know why it's an anomaly. It's just the routine has picked it up. And what I'm thinking of next is how do I build an agent that can sit with a SME and help them discover why that was an anomaly? Because just with this data, it's pretty hard. Now, the more I've been reading about is that they talk about, you know, if you fill out a claim, let's say you're filling out an accident claim, and then they're using LLMs to look at the language that you used for a car accident. And they basically have these LLMs have structures or vectors around what do you typically use when you talk about a car accident, or when you go for uh, a cancer treatment in a hospital, what is the language that the doctors use? And when you don't use those words or you misuse the words, then they can start picking up on it. So that gets to the next step of saying, well, shucks, this data doesn't look right. What other indicators can we help the agent or the SME to understand that the data is funny?
Mm. Yeah, that really, so I'm also thinking about a specific project I worked on where we had that problem. Somebody did anomaly detection and then said, okay, please check if these are the
Yes.
right fields. And we're like, we actually don't know.
Yes.
We've also just applied an algorithm. So that then became, I suppose, an ethical dilemma as well, because you have to be able to justify, to say why these things are flagged.
Okay, so where it's not really an ethical issue. What the process you'll take is, and that's why I equate it to the reasonableness thing. A reasonableness dimension in DQ, when I pick up something's unreasonable, it doesn't mean that it's wrong. It just
Yeah.
doesn't fit a pattern. So please don't tell the customer that you're wrong. Please get an SME to investigate, pick up the phone, look at the video recordings, look at the photographs that were taken, try to see if something's wrong, and then finally you'll declare it as either a false positive, that you've actually done this thing and they've double checked and they can't find anything wrong with this. This is actually quite right. And then you go back into your model and you label it to say, this is okay. This is not an anomaly. And then you train the model again to detect that that's an all right pattern. Does that help?
That is very helpful to also say, like, it's a I want to say a labor intensive process as well. Not necessarily from the algorithm perspective, but to check to verify that certain things are correct or not correct to make your algorithm better. Okay. Thanks, Howard.
Right. And now, of course, what we're going to argue is a case of if I was checking every single claim, now I'm just checking the anomalies. I'm not checking every. So you're getting those the benefit of not having to look at everything, but they're getting harder and harder to explain. So
But
now
then at
you're
least
really
we're
being
focusing on the ones that actually need the time and energy to focus on,
correct.
and not on just everything.
Yes, correct, 100%. So you're really narrowing it down, and your SMEs are having to get cleverer and cleverer and having to teach the model more. Yes, William.
One of the things that I've noticed, and I think you and I picked it up because it's all about context. I mean, when I was up there with you, you need to structure your sentence to let people know that you're not actually saying that this is wrong. You're saying that there's a system that you're using, and it has picked up something, and you need it investigated.
Right.
And when you use the word investigate, people feel a little more comfortable.
You're right. You're right. And they don't go in there expecting a fight.
Yeah, exactly.
So that's
exactly.
Yeah, that's where the police had a problem in the US, where they were being told that this is a criminal, and so they get out of their car in an aggressive mode, expecting a fight. And that's where your confirmation biases start to kick in and stuff like that. So yeah. Yes, Paul, PG.
Just want to mention something based on what Esti said is so the algorithms is picking up that there's a pattern issue, there's an anomaly in the pattern, and the human needs to come into play. But in the example that I had a month or so ago, when I was defrauded on my bank account, and there were transactions going off. At some point, the system needs to apply the human, pull in the human, but there's also a big cost involved, right? So if everything that was picked up as an anomaly was sent to an internal investigation team, it would have been a great cost. So that's why they let the transaction through, but they phoned me. They let me know, and they put the onus on me to actually be the human.
Yeah, that's right. That's right.
And the cost of them, and the cost of them repaying me was cheaper than what it would cost to investigate every possible anomaly.
Yeah, and I suppose that's a good thing is possibly it's quicker to get your take on it. But I suppose when you're claiming for money, then you're probably not going to be honest about it. You are claiming for that someone else is taking your transactions, but maybe when you filed an accident report that actually your kid had and you didn't have. So yeah, that's different scenarios as to yes, JB. Yes, Johan.
All right, Howard. Now this is, I guess I'm going to try and formulate this question very simply. Okay, your example here was of, say, the insurance industry and a claim.
Yeah.
Right. Say now, for instance, now this gets now a little bit more hairy. We're looking at the health insurance. Okay, health insurance has got claims as well, and it's also got patient information. All right, and health insurance claims, or if you look at health, users would use a lot of actually prescriptive AI as well compared to generative AI. Okay, so now just also actually iterating what ST talked about, like ethics, things like that, security and things. How's all these, what bothers me, because I'm looking at from a data architect, security, data and stuff, like how is this going to impact if we start doing these models and outliers, but you're doing it on a claim. Say you're doing it on claims because you want to try, because I've worked in ag health with fraud as well, because you want to tap into fraud, but now you're also using the people's health information as well. Or is that maybe you may not use it? So those are some really, because also from a governance point of view, like how do you decide on these things? Or
No, sure. And I think that's all part of that feature selection. They call it feature engineering, and where you need the appropriate governance in there to say, you're doing something that wasn't part of the purpose that how the patient submitted to you. So they gave you the data based on that purpose, and you're not using it for that purpose. So then you are certainly picking up a privacy thing. But I don't know if Mario's on, but that responsible AI, it's very clear on what's the business value that you're getting out of it, and what's the value back to the customer. So you have to balance these two things, and you go through a process of assessing that. There's something called EU AI Act, and they talk about this balance that you have to achieve. And we had a lawyer on about a month and a half ago, and they were saying, guys, this is what we need to be paying attention to. So that's how do we choose the features that we can use to train the model? And are we giving the customers the value back? Like I'm talking about here is the quicker I can pay out the customer, the better for the customer. So our aim is to get the customer's money paid out as quickly as possible. That's what our aim is. And you'd have to constantly check, well, is that what you're doing? Is that the purpose behind this model?
Okay, see, because actually what I'm just worried about, you get this AI, you say for instance, now this is a very sort of a very or just a quick sort of thing. A person has got cancer, they're doing all these claims and things like that, and suddenly there is this AI, this Gen AI, the fraud, the fraud aspects picks up some fraud, and someone contacts the customer, and they just a poor person dying of cancer, and now they actually kind of someone is calling them because there's some fraudulent transactions on your say a 1 million already what you've already claimed. I'm just thinking about, so what is that? Okay, that could be a nightmare for a company when that comes, I think, so that's what I'm just kind of alluding to. Yeah.
So we need to be paying attention to all of those corporate governance, AI governance, AI on your systems. So we need to be having the appropriate controls in place and asking those questions. We always need to have that in place. What I suppose what I'm focusing on, and that was part of last week's talk, is about how do we balance data privacy, AI models, LLMs,
right, I missed that one.
All that type of stuff. Yeah, so this is more about how can I use the algorithm to help me check the quality of the model, of the data, of the anomaly, and speed up that process.
Cool. Okay, thanks. Actually, I'm a bit slow actually behind the time.
No problem.
I try to ask the relevant questions. Thank you.
Understand. Yes, William.
So we've got a flag for our customers to say you may or may not use my information for automated decision making, right?
Yeah.
Does this new era that we're going into, does it require another flag to say you may or may not use my data for training? Or is it a case of if a person said you can't use my data for automated decision making, then those records have got to be excluded?
William, I think there's two different scenarios. The one challenge is saying basically where the customer is saying, I do not want you to make automated decisions on my behalf or about my data. Yes. Because you don't trust it. The other one is to say, if I'm collecting data and I remove the PII and the SPI and the personal identifying information, and I'm just dealing with features like I've shown you there. In terms of that situation, that's the company's data.
Yes,
I would still be able to hold on to that data. Even when someone tells me remove my data, I can remove the PII. That doesn't mean I need to remove all the transactions and the claims that person had, given that I don't have any way to re-ID the person. Remember, it's about re-ID.
No,
I can de-ID you, but I can't re-ID you. That's the challenge.
So in that scenario, should we pick up that this is an anomaly, the problem is we've DID. So we can't go back now and contact the client or anything like
You
that.
know what, William, I certainly feel that this should be part of the model development, right? So if you're talking about
yes.
data 5 years ago, well, then I should be ironing out those issues. If I run the training model and it says I got a problem with this guy, well, maybe, you know, we check it out and we say, well, okay, maybe that should be set to be a type of anomaly, right? Where that we can't resolve it. Yeah.
Interesting. New world, right?
Yeah. Guys, I need to go. I need to go to the airport. Are there any other questions, any comments? I mean, I'm hoping you're getting excited as I got when I saw, wow, it's amazing how powerful this is to do this type of data quality checking that I've never really experienced. Yes,
Well, the point is we were lost before. Oh, sorry, Johan.
No, fine. I guess I just wanted to actually iterate what was said. So I just because I put that in the comments, I don't really want to actually interrupt. But so like with all this PII and things like that, so would actually, if your data is masked actually properly, then should that be okay for most of these to use that data in the models? Okay, because that's, for me, the type of questions as a data architect which a lot of people are going to ask.
Yeah,
And that's always going to come up. Yeah.
What is always there is when you DID, you have to be able to prove that you mathematically can't re-ID. Okay, that's the given. I can keep the aggregated information as long as I can't re-ID the person. That's the line. So, for example, if and this was always the example used, if I'm sitting in a small town in America, I know I've driven through some of them on a motorbike, and they said they got 123 people. And in the 123, there may be only two 80-year-olds. It doesn't take a lot to re-ID that person. So can you ID by age bins or age brackets or whatever it is? Mathematically, you have to go through the process of saying it can't be re-ID'd. So that's the challenge we face.
Cool. Thank you very much. That was that cleared up some of my sort of burning questions. Thank you.
Great. Yeah, Esti, I think that harmonic mean is fantastic in terms of saying, well, we've always sort of thrown away the mean because you got the skewers, the guys that get skewed, but now you're applying it in a different way. I think there's, you learn there's a different approach to that.
Yeah, we had a lecturer that always used to say a mean without a standard deviation doesn't mean much.
Yes. And now
I think you would quite have liked the harmonic mean.
And there's actually something that I wanted to show you, and that's in my, sorry, it's actually, let me just show people quickly. That's that Z score. And that Z score is really something else in terms of what it's showing you. Shucks. I think this is it. Go. Okay, so this is all splitting, where you split the data. Okay. Coding the split, validating the split, and then normalizing the claim. So I don't know if you've heard of something called Z-score, which is Z is equal to the actual value of the record minus the mean over the standard deviation. Okay, and then you standardize the data. So, and then what you can do is to say, well, if that Z-score, the absolute value of the Z-score is greater than 3 deviations, you probably got a challenge with your normal data. You got a problem in your normal data. So what you can see, what the Z-score does for us is it takes it anywhere between minus 20,000 and plus 20,000, and it creates it from -5 to 5. And there's your density. So you can see this is your normal data that kills the histogram, and then you come down to the Z-score, which it extenuates the differences between these things. But now you can start comparing claim amount, claim duration, claimant age, because they're very close to each other on the graph. Can you see how that standardization reduces the impact of these big outliers?
Yeah.
So this is really powerful. Getting everything to a Z-score is extremely powerful. I mean, this so difficult because I've got 100,000 sitting here and I've got 20 over there. So how do I get it into a standardized view and you make use of this concept? So all of your training of your models must use the Z-score, not the original amounts.
Makes sense.
Okay. Great.
Well,
Guys,
Howard, fantastic. Thank you very much. We're going to have to call you professor from today onwards. But yeah, very, very good. And fly safe, eh?
thank you very much.
Cool.
Thanks, everybody. Cheers.
Yes. PG, are you
Thanks,
staying?
Thanks,
Hey.
Howard.
Yes.
Thank you.
everyone.
Very exciting.